The velocity recovery function, or VRF, describes the effect that previous action potentials have on the speed with which subsequent action potentials travel down the muscle fiber. An understanding of this somewhat esoteric physiologic phenomenon is important in performing and analyzing the results of single fiber EMG recordings. Action potentials of two muscle fibers innervated by the same axon reach the recording electrode at different times. This is due to the different distances of their end plates from the recording electrode and to the difference in the action potential propagation velocity in the two muscle fibers. With the electrode in a stable position, the distance between the end plates and the recording electrode remains constant from one motor unit discharge to the next. If the propagation velocities in the fibers are constant, the variability with which the signals reach the electrode is due to the neuromuscular jitter. However, the propagation velocity in one or both muscle fibers may change due to the effect of the VRF. And this can change the time at which one or both action potentials travel down the muscle fibers to reach the recording electrode, in which case the apparent jitter would be increased. This can be described schematically. The time difference between two successive discharges of a motor unit is the interdischarge interval, or IDI. The IDI is the reciprocal of the firing rate. When the IDI is 200 milliseconds, the firing rate is 5 Hertz. At 100 milliseconds, the rate is 10 Hertz. The interpotential interval, or IPI, is the time between two action potentials from muscle fibers in the same motor unit. In this plot, the IDI is shown on the x-axis, and the conduction velocity in a muscle fiber is shown on the y-axis. In this example, the muscle fiber has a baseline conduction velocity of 3.7 meters per second. When the IDI is very short, the muscle fiber is in a subnormal state and conducts the potentials at a slower speed than at baseline. Such short IDIs could be seen only when activation is produced with high-frequency axonal stimulation. At lower firing rates, the IDI becomes longer and the muscle fiber is in a supernormal state and conducts the potentials faster. The supernormal state decreases as the firing rate slows further, and in this example, the conduction velocity approaches the baseline value, 3.7 meters per second, when the IDI is 200 milliseconds. But it may take up to 1,000 milliseconds in some muscle fibers. The relationship between the IDI and the action potential velocity in this muscle fiber is described by this curve, which is the VRF for that fiber. The VRF varies from fiber to fiber and is pronounced in 50 to 75% of muscle fibers. The latency changes due to the VRF are seen more prominently in later action potentials, which suggests that they are mainly due to the distance between the end plate and the recording electrode. If the IDI is constant, that is, the firing rate is held steady at either a fast or slow rate, the conduction velocity in the muscle fibers is usually constant. However, if the firing rate changes from one discharge to the next, the velocity may also change and could affect the interpotential interval, depending on the VRF in the originating fibers and the distances of their end plates from the electrode. The VRF can be appreciated by observing the effective stimulation rate on the stimulus response latency during axonal stimulation. In the following video, the axon is being stimulated at 5 Hertz initially, and the sweep is triggered by the stimulus, the artifact of which is here on the left. Watch what happens to the positions of the two tall spikes at the right as the firing rate is increased to 10 Hertz. As the firing rate increases, they shift to the left, indicating an increase in their conduction velocities. see the signals recorded at each of the two firing rates. Note that the latency of the latest two action potentials shortens, but that of the earliest does not change, indicating little VRF in that fiber. Note also that the latency shortening is progressively greater in the potentials with the longer latencies. In this plot of the sequential IPIs of the last potential, we see how the latency shortened as the stimulation rate increased. If we look at the IPI values before and after the firing rate changed, we see that the distribution of interval values is equally tight in both periods, indicating that the jitter is the same at both firing rates. Here we show the calculated jitter during the shaded time segments, confirming that the MCD is essentially the same and is clearly within normal limits at both stimulation rates. However, if we measure the jitter during the transition period between the two rates, the variation in interval length introduced by the VRF introduces extra junctional jitter into the calculation, which is now double the other values and would fall above the normal range. This is why it's important to measure jitter at a constant stimulation rate and after the initial 1 to 2 seconds after beginning a train of stimuli or after changing the firing rate. The effective firing rate can also be seen during jitter studies performed with voluntary activation, as will be shown on this diagram. If the two muscle fibers have different VRF values, at slow firing rates, when the VRF effect is less and propagation velocity is lower, the IPIs will be longer. As the firing rate increases, the VRF effect is more pronounced and the IPI will shorten. If the firing rate is not constant, the VRF effect will vary from discharge to discharge, depending on the VRF in the originating fibers, the distance of their end plates from the recording electrode, or both. This adds variability to the IPI values, which increases the calculated jitter. To avoid this, the firing rate should be kept as constant as possible for jitter analysis. This requires the subject to maintain a steady force of contraction. In the following video, listen to the jitter and also the variation in the firing rate of the motor unit. You can also hear a humming sound due to electrical interference, but it's not high enough to affect the jitter measurements. Here all the traces are superimposed. The traces are triggered on the second potential, which thus appears at a fixed position on the screen. There's little variation in the position of the non-triggering first potential, indicating normal jitter between the two potentials. This plot shows the relationship between the IPI and the IDI in these potentials. When the IDI is less than 100 milliseconds, the rate is greater than 10 Hertz. And when it's greater than 250 milliseconds, the instantaneous rate is less than 4 Hertz. This plot shows a firing rate that varied from more than 10 Hertz to less than 4 Hertz. This variability in firing rate could also be heard on the loudspeaker. When the firing rate decreased, the interpotential interval increased. And this is the effect of the velocity recovery function. The MCD for this recording is 22 microseconds. The MSD, the mean sorted difference, is a calculation that reduces the effect of the firing rate variation that's produced by the velocity recovery function. The MSD value here is 16 microseconds, and this is less than the MCD. And we use the lower of the two calculations, 16 microseconds, as the jitter. The effect of the velocity recovery function is seen more easily when the interpotential interval is longer. This signal contains 3 time-lock potentials. The interval is short between the first 2 potentials and long between the second and third. We will trigger on the second potential in the following video. Here all the traces are superimposed. Potential 2 appears at a fixed position since it was used as the trigger. Potential 1 shows a tight superimposition indicating normal jitter between number 1 and number 2. There is some variability in its amplitude due to slight needle movement during the recording. The calculated jitter between the first 2 potentials is 13 microseconds, and the mean interpotential interval is 482 microseconds. There's no significant relationship between the IPI and the IDI. The MCD and MSD values are similar. The MCD is used as the jitter since it is slightly smaller. The third potential also shows good superimposition, indicating normal jitter between it and the triggering second potential. However, the rising slope looks thicker than the rising slope of the first potential, suggesting greater jitter in potential 3 than in potential 1. The MCD for potential 3 is 29 microseconds, compared to 13 microseconds for potential 1. This is consistent with our visual impression of the jitter. The mean interpotential interval is 5,385 microseconds. In the IDI-IPI plot, we see that there is a strong correlation between the interpotential interval and the interdischarge interval. The velocity recovery function gave shorter interpotential intervals when the interdischarge interval was small. This effective firing rate was partially compensated by computation of the MSD, which is slightly more than half the MCD value. The jitter is thus recorded as 16 microseconds, the value given by the MSD. To determine whether to use the MCD or the MSD values to represent the jitter, some laboratories use MSD when the MCD-MSD ratio is greater than 1.25, but the smaller of the two values is used here. Thus the MCD was used for the first pair and the MSD for the second. This slide shows how the VRF effect alters the interpotential interval after a block and thus affects the calculated jitter. The recording was made during axonal stimulation at a constant rate, and the stimulus intensity was deliberately reduced below threshold at this point to simulate a block. The third trace in red shows this epoch. The following stimulus response interval was considerably longer than the others because the preceding interdischarge interval was twice that of the other responses. The longer interval that followed the block can be seen well in the top trace. The VRF effect thus artifactually increases the jitter when there's pathologic blocking, making the jitter calculation less robust in that circumstance. A detailed discussion of the VRF can be found in Chapter 8 of the Single Fiber EMG monograph.